My name is Ethan Sifferman. I am a lecturer at UC Santa Cruz, and I've spent a lot of time with open source tools, and I've been trying to incorporate open source tools into education as much as I possibly can. So about me, yeah, currently at UC Santa Cruz. That's my GitHub and my email. Feel free to contact me. And while I was at UC Santa Barbara, I just finished my master's from there. My master's thesis was on education using open source tools. So feel free to read my thesis. I worked really hard on it. And I like to contribute to open source tools in my free time, although I have much less of it now that I'm teaching. But cool. So usually when you teach hardware, usually go from a bottom-up approach. Almost like Legos. Like you learn maybe first what a transistor is, and then you go up and you learn what a gate is, then maybe build a full adder, and then next you learn Verilog. And that jump from gates up to Verilog is a little bit challenging because if you look at, so this is a behavioral implementation of the floor of the log function base 2. You got if statements, and it's all kind of confusing. It's hard to tell for students what is synthesizable, what are synthesizable constructs, and also what's simulation only, and what hardware will be generated. And so this may inspire you to decide, I'm not going to teach Verilog. Yeah, we're gonna use Verilog, but I'm not going to teach it. Instead, we'll just kind of have a bunch of standard cells. Students can use these you can't see my mouse, but you can use XOR gates, AND gates, and stuff. And then maybe you instantiate your full adder module. But this is good. All right, it's very clear what hardware is being generated, but it's not really scalable. And this is a reason why Chisel and other languages are more popular, or are becoming popular, is because we want something that's easy for people to write, but also can be used to generate hardware at a scalable level. Just really quick, does anyone know a better line of Verilog that we can include that will kind of remove a lot of this boilerplate? This is a 4-bit adder implementation. Does anyone know what we can do? Yeah.
Continuous assignment of data flow, a shut-in behavioral model?
Yeah, so you can use an assign statement, yeah, and you can just use a plus sign. So in my opinion, this is way simpler, and I really like doing this. So in my opinion, I think that Verilog should be taught from a behavioral perspective, as exactly what was said. But it's difficult to teach Verilog from a behavioral perspective generally, but it becomes easier with open source tools. And the first thing that I've really tried to focus on is building good auto-graders for students. And the next thing is by using netlist viewers for students so they can actually see what hardware is being generated when they type out some Verilog. So first, anyone use GradeScope for, if you're an instructor and use GradeScope or something? Yeah, so GradeScope has a really awesome auto-grader system where you can provide a Docker container, and then it'll run whatever simulations and things that you want done. And another just great thing about software, so this is now leaning into is FPGA design software or hardware. It can be used as software from the perspective of education, because I know that my partner, she's an English major, and I'm sure would have killed to be able to just submit to an online portal her 20-page essays, and then it would perfectly say all the things that are wrong with it and show all the failing test cases and linting and all these awesome things. We should be, as instructors, we should be digging into auto-graders as much as possible because we can automize all this feedback. And what was that? Sure, yeah. It offers much more feedback for students more rapidly and generally more higher quality than what would be given if it was maybe a TA just kind of looking at student code versus an actual linter going through and looking at it. Yeah, so really quick, I'm sure you all know how to use open source tools, but this is the flow that we've chosen in a lot of my auto graders for the classes I taught at UC Santa Barbara. So students submit a Verilog file, and then it's linted, and then it's run against a test bench. And then the Verilog is also synthesized, and then a gate-level simulation is run, and then the Yosys utilization and next PNR timing reports are generated, and those can be, those can be graded. And this is just a quick little display of what an auto-grader result would look like. You can see that the top one is a lint test where the student mismatched their widths on some net, so they're getting a warning on that, and we say you don't want any warnings or else you will fail this test. Then below that, there's a couple just quick test benches where we provide some feedback. You can't really read it, but it's saying that one part of their code isn't working. And then you can see at the bottom that they're at least passing one test, which is just a quick synthesis test. Great. And then another cool aspect of GradeScope is that you can have leaderboards. So now you can say, try to get your logic count to be lower than your friend's logic counts, or try to get your clock frequencies higher than others. And generally, this isn't the best. This isn't always the best metric, especially when using Yosys, because maybe that encourages kind of really weird Verilog. We got one implementation that was completely not readable at all. And yet, it got 13 logic cells, and it was kind of funny because the code itself was terrible, but it was better by this metric. So anyways, kind of funny. Great. And at UC Santa Cruz, we are currently working on trying to create a more generic framework for Verilog auto-graders, and maybe in the future latch-ups, we will talk about that. Cool. Okay. So assuming that students have now submitted their code and it's been auto-graded and it's really fantastic, you know for certain that this code could be used on a real chip. We need to remember, wait, no, hold on. This isn't a Verilog class. Remember, this is a digital design class, or it's an architecture class. We need to be sure that students are learning what is happening under the hood. And when you're writing for loops and if statements, it's a little bit challenging for students to grasp that. However, has anyone heard of DigitalJS? Really? Okay, this is the coolest thing I've ever seen ever. So this is a website, DigitalJS Online. It's running DigitalJS and also Yosys. What you can do on this website, and there's also a VS Code extension, you can put in on the left side, you can put in some Verilog files, and then it will synthesize it, and then use elk.js to display it in this nice schematic viewer on the right side. And you can even interact with this. So you can go and change values, you can click buttons, and it will run the simulation. And this is it's a great interactive way of teaching what synthesis is. Another thing is, there's a popular Verilog to schematic tool called netlist SVG, and I saw a few other people have been using it in their talks. In my opinion, this tool, DigitalJS, gives much clearer schematics than netlist SVG. I really like this tool. Anyways, I didn't create it. Is the creator here by any chance? Is anyone? No? Okay, yeah, maybe next year. Okay, and then, so I was going to say, so this is a file that we gave to students, and we asked them to try to create a more human-readable diagram, go and draw a circuit diagram. And this is what a student drew after they kind of looked at what the DigitalJS output was. And yeah, so this is a find first set algorithm, if you're familiar with that. So yeah, very cool. Here's just another example. So you can put in anything you want. You can see a flip-flop is being inferred there. And yeah, all very cool, very cool. Yeah, you can use commercial schematic viewers as well. I have a couple, whatever. I ran just an inverter design, and you can see here I have QR code if you want to look at how to create schematics using the different commercial tools. But I find that DigitalJS is far superior than the commercial tools for schematic viewing. Yeah, so by teaching students now the better intuition for synthesis, then now we've prepared students better for industry, and now they can use Verilog as a creative outlet, and they are able to do more advanced problems now. So for example, if you remember my talk from last year, I gave a lightning talk about UC Santa Barbara's advanced architecture course, where we had students implement a branch predictor and implement a victim cache and do a program to do out of order and virtual memory. And this was only possible because, by the way, this is all adding on to the CVA6 RISC-V course. So they had to go in and they would make these changes, and then there were assignments based on this. Nothing was pushed to the actual like CVA6 repo. This was all like in the class, but yeah. But students were able to do this because they had the background in behavioral Verilog. So that's this whole kind of, at least beginning of this talk has just been, I'm a big advocate of behavioral Verilog because it opens up a lot of doors for students. Okay. And just in the last like closing minutes of my talk, I wanted to show just another couple other kind of fun things. So does anyone know what this is? What is this circuit? Yeah, it's a D flip-flop. Yeah. It's not a very good one, though, right? It's got tons of NAND gates and stuff. However, those two textbooks, they say that this is what a D flip-flop is. And yeah, I'm not the biggest fan of that. So guess what? You can go into the Skywater 130 nanometer PDK, and you can look at the actual transistor layout of at least their D flip-flop. And this is super cool. So if you're teaching a VLSI course, you can pull up the PDK of Skywater 130 and just show the actual transistors in each standard cell. And I also wrote a little script here that will kind of combine related transistors into a more like viewable schematic. You can see that there's transmission gates and tri-state buffers and inverters that it will kind of infer. So feel free to look at that if you want. And then I then took that tool and made this nice visualization of like a real flip-flop schematic instead of the NAND gates. And this is a cool little website that I made. It's called Flip-Flop Visualizer, and I have it right here. And you can like slide around. Oh, all right, you can't see it. That's okay. Well, you can slide around each of those little things at the top, and you can change the inputs of the flip-flop and see how a flip-flop will react. So highly recommend going and checking it out. I worked pretty hard on it. And the final thing I want to plug is, all right, it's broken. Nice. Okay, final thing I want to plug. I've recently created a YouTube channel because I feel like there's a kind of a big gap in Verilog education on YouTube. And unfortunately, there's still a big gap on Verilog education on YouTube because I only have 3 videos. But, yeah, I'm a big fan of the YouTube channels by Pat and Matt. Yeah, my Verilator video has over 800 views now. Very exciting. And whatever, and I try to incorporate open source tools as much as possible. So, and I also have a video on flip-flops where I use the flip-flop visualizer. So, yeah, thank you so much, everyone. That was just a little bit of what I've been working on as an educator using open source tools. So feel free to talk to me afterwards, or I'm happy to take questions.
Love your work, Ethan. This is good. And just a comment, not so much a question. It's very encouraging to see how much open source EDA is getting used in education these days. It's like, I don't know, when did I do my degree? Early noughties. And it was just like a shit show of mentor tools and like, oh my God, it was dreadful. Anyway, I wish I had this. I wish I had all these amazing web-based tools and open source EDA tools. I reckon I would have been way more, like, I eventually became enthusiastic about this, but I can just imagine students now kind of get it quicker and can get their hands in there, like on their own time, right? Instead of like going to get some cracked version of Model Sim off BitTorrent or something, which I may or may not have done, I'm not sure. But a friend probably did that, yeah. Anyway, yeah, this is awesome to see, so thank you for your work.
So have you fixed the issue? Yeah. It's easier.
So have you fixed or solved the issue of autograders not being able to enforce stylistic practices, commenting, or even now the biggest threat of ChatGPT generated solutions? Did you find a solution to that with your autograder, or what did you do?
What was the first thing that you said?
So one of the things I do in my class is I enforce stylistic pieces
Oh,
to make sure
yeah.
that they know continuous assignment versus behavioral, benefits of each. Commenting, because we all know legacy code is nightmares. Have you found a solution to auto-grade that stuff?
Yeah, that's a really good question. One thing that at least I try to enforce is as much of the low-risk coding style as much as possible. And there's no perfect solution, but I try to use Variable. Variable has a lot of stylistic things that you can include in its whatever configurations. It's not perfect. I made an issue on Variable like whatever a year ago. It's still not been finished, but I feel like that's more on me at this point. Yeah.
I think this has a lot to do with what we see as people come into open source communities also, not just from a university perspective, is that people come in expecting, with the question, I want to learn to write Verilog, not I want to learn digital design. And there's the idea that, okay, you can just type programs into a file named .v, and you can write C in Verilog. And so I guess one of the questions that I have is, do your students come in with a lot of experience in software design that they incorrectly try to apply? Do you catch them early enough that they don't have to unlearn this? Or do you have tricks for having them unlearn this?
It's a super interesting question. So that's one half of the question. Then the other half is there are people who have never written software at all. And they're just like, they've never seen a Unix terminal. And so Verilog is just a super multidisciplinary area. And it's hard because you have so many people from all different aspects, specifically software people, though. That's why I think it's crucial. So for me personally, anytime I write Verilog, I make sure that I also provide the schematic. It's like a Verilog without a schematic is, treat that as like simulation. Treat that as like a program. If I include a schematic, it's like this is very clearly like, this is what the Verilog is actually like creating. I think just trying to link that as much as possible is crucial. Yeah, and that's kind of what I've found helps software people the best. Yeah.
Hey, thanks for the talk.
Yeah.
Yeah, I didn't know about DigitalJS. I will check it out. Have you tried XDot? No, I'm just kidding.
XDot.
No, don't.
Okay.
The little thing in Yosys. Anyways, my question was, you were talking about looking at the spice from Sky 130,
Yeah.
and then you had a visualizer. Did you create that? Did you have to do that?
Yeah, don't look at the source code though. It's really like kind of nasty. Yeah.
Okay, because I'm usually going the other way, from schematic to spice, but I would like something like this. So that's
Yeah.
released?
Yes, it's released. Yeah, that's the QR code for it.
Oh, I can't read that, but we'll talk later.
Sure. Yeah. Yeah, we can talk.
Thanks.
Any last questions before we call time? Okay, that's probably it, Ethan. Thank you very much. Great
Thank you.
presentation. Thank you.